In this class, we will discuss about valence bond theory, VBT. This theory was put forward by Pauling and Slater in 1931. Pauling and Slater, valence bond theory in 1931. Linus Pauling. And Slater in 1931. Pauling and Slater in 1931. And this theory tells us about the formation of a covalent bond. Covalent bond formation between atoms in a molecule. So according to this theory, a covalent bond is formed by the orbital overlap. Orbital overlap. Covalent bond is formed by orbital overlap. This is the term, orbital overlap. According to Lewis, a covalent bond is formed by mutual sharing of electrons. Instead of mutual sharing, orbital overlap. That is VBT, valence bond theory. So we can take a simple diatomic molecule, hydrogen. Formation of hydrogen. So hydrogen atom, atomic number 1. Configuration 1s1. Another hydrogen atom, atomic number 1. Configuration 1s1. So 1s1 means a spherical orbital with 1 electron, and this is also a spherical orbital with 1 electron. Both are unstable. Hydrogen atom has a deficiency of 1 electron to achieve the stable noble gas configuration helium. What is the configuration of helium? Atomic number 2, 1s2. It is highly stable, s orbital, 2 electron fulfilled, 1s2. S electron, 2 electron fulfilled. This is a half-filled orbital and this is unstable, and this has a deficiency of 1 electron to achieve stable helium-like configuration. The similar discussion for this hydrogen atom also. So two hydrogen atoms come closer and these two orbitals overlap each other, and two orbitals overlap each other, and a pair of electrons, and 1s1 becomes 1s2, and this 1s1 also becomes 1s2. Both H atom acquire a stable noble gas configuration and H2 molecule is formed. And this H2 molecule is stable because in H2 molecule both atoms acquire a stable noble gas configuration like that of helium, 1s2, 1s2. So H atom is unstable, H atom is unstable, but H2 molecule is stable because both atom, the 1s1 configuration becomes 1s2, half-filled orbital becomes full-filled, they acquire stable helium-like configuration. This is the and a covalent bond is formed between two H atoms. So how a covalent bond is formed? A covalent bond is formed by the orbital overlap. Orbital overlap containing unpaired electrons, half-filled, with opposite spin. One of the electrons is moving in the clockwise direction and another electron is moving in the anti-clockwise direction. So minimize the repulsive force, clockwise and anti-clockwise, and a covalent bond is formed by orbital overlap, and this is VBT. So this theory is also known as Pauling-Slater theory, put forward by Linus Pauling and Slater in 1931. And this theory tells us about how a covalent bond is formed. A covalent bond is formed by the overlap between atomic orbitals containing unpaired electrons with opposite spin. And this is the formation of hydrogen. Here two s orbitals are involved in the overlapping, and this overlapping is called SS overlapping, symbol overlapping. a diatomic molecule. So we can take another diatomic molecule, halogens, fluorine, chlorine, bromine and iodine. So this is SS overlapping. Another example, formation of halogens. We can take a fluorine as example, F2, a diatomic molecule. So fluorine atomic number 9 and the main shell configuration is 2,7. So it has a deficiency of 1 electron to achieve the stable noble gas configuration neon. What is the configuration of neon? 2,8. So fluorine has a deficiency of 1 electron. Not only fluorine, for all halogen, outermost shell contains how many electrons? 7 electrons. So all halogen have a deficiency of 1 electron to achieve a stable noble gas configuration. That is why in non-metals, all halogens are highly reactive because they have a deficiency of only 1 electron to achieve a stable noble gas configuration. So orbital wise configuration, 1s2 fully filled orbital, 2s2 fully filled orbital and 2p5. 2p5 means 2px2, 2py2 and 2pz1. And these are full filled orbital and this is the half filled orbital. And the fluorine has a deficiency of 1 electron in this orbital, 2pz orbital, half filled. This becomes full filled. When this becomes full filled, 2,7 becomes 2,8 and the fluorine achieve stable noble gas configuration like that of neon. So another fluorine, its atomic number 9, its configuration also ends with 2pz1. So when two fluorine atom, 2pz means a dumbbell shaped orbital with 1 electron. And this 2pz means a dumbbell shaped orbital with 1 electron. So when two fluorine atom approaches this half filled orbital and this half filled orbital approach each other and they get overlapped like this. And this overlapping is called PP overlapping and a covalent bond is formed with a pair of electrons and F2 is formed. In the same way, chlorine is formed. In the case of chlorine, the valence orbital is 3pz1 and 3pz1. Two dumbbell shaped orbital overlap. So in halogens X2, XX overlapping is PP overlapping. In fluorine, we can see 2pz overlapping or PP overlapping and a covalent bond is formed. So how a covalent bond is formed? A covalent bond is formed by orbital overlap containing unpaired electrons with opposite spin. And this is a simple diatomic molecule, fluorine. So another example, formation of hydrogen halides. Hydrogen halides, HX. So we can take hydrogen fluoride. So hydrogen atomic number 1, configuration 1s1, spherical orbital with 1 electron, half filled, unstable, deficiency of 1 electron. Fluorine atomic number 9, configuration 2pz1 as discussed before. So a dumbbell shaped orbital with 1 electron. When H and fluorine approach each other, these two orbitals get overlapped. Orbital overlap. A pair of electrons and HF is formed. And this overlapping is called Sp overlapping. So HX is formed by Sp overlapping. Hydrogen fluorine overlap, S and 2pz. H and Cl, S and 3pz orbital. And a covalent bond is formed. So again, how a covalent bond is formed according to Linus Pauling and Slater or VBT by the overlap between atomic orbitals containing unpaired electrons with opposite spin. And this is the valence bond theory in the case of simple diatomic molecules and orbital overlap. So we can discuss some. So before that, we can discuss about different types of overlapping. Different types of overlapping. So SS overlapping, this is SS overlapping, a pair of electron, SS overlapping, and this is PZ overlapping, PP overlapping, and another is Sp overlapping. And this is also a PP overlapping, a pair here or here. PP overlap. So this is a PZ, then we can say this is a PX. when PZ orbitals overlapped, when PZ, Px, Py and Pz. When PZ orbital overlapped in a head-to-head manner, the remaining orbital cannot overlap in head-to-head manner. They overlapped in parallel manner, another two orbitals. So here 2PZ overlapped in a head-to-head manner. So 2p orbital, 2px, 2py, 2pz, three orbitals. 2px, 2py, 2pz. When two atoms approach each other, 2pz and 2pz overlapped in a head-to-head manner like this. The remaining two atomic orbitals can overlap only in a parallel manner. This manner, px or py can overlap only in a parallel manner because these two orbitals overlapped in a head-to-head manner. Then these two orbitals cannot without breaking this orbital. So when two atoms approaches, when two fluorine atom approaches, 2pz and 2pz orbitals overlap in this manner. Any other atom, not fluorine, any other atom. When 2pz orbital overlapped in this manner, if these orbitals are with half-filled electron, if these orbitals are half-filled, or these orbitals are with unpaired electron, one electron in this orbital, one electron in this orbital, they overlapped in a parallel manner and a weak pi bond is formed. And this orbital containing one electron and this orbital also contain one electron, they overlapped in a parallel manner. And this is a sigma bond, this is a strong bond, and these two bonds are weak pi bonds. So pi bonds are formed after the formation of a sigma bond. This is head-to-head manner. The other two orbitals are overlapped in a sidewise manner or parallel manner. So orbitals can overlap in two different ways. These three orbitals are in a head-to-head manner, head-on-head collision like accident head-on-head. So this is a head-to-head overlap. And this is a parallel overlap, sidewise overlap. And this is a maximum overlap. And the covalent bond formed is very strong because this pair of electrons are present in the nuclear axis. This is the positive center nucleus. This is also the positive center nucleus. So this pair of electrons are in the nuclear axis. A very strong intimacy, a very strong attraction between these two electrons and these two atomic nuclei. Positive center nuclei attract negatively charged electrons. So a very strong attraction between, a very strong intimacy between a pair and these atomic nuclei. That is why this covalent bond formed is very strong. Such a strong bond is called sigma bond. So orbital overlap may be head-to-head or sidewise. If it is head-to-head, overlapping is maximum, and the pair of electrons are in the nuclear axis. So much intimacy between this pair of electrons and atomic nuclei, and the covalent bond formed is very strong. Such a strong bond is called sigma bond. Here, these are the atomic nuclei, and this pair of electrons are not in the nuclear axis. They are far away from the nuclear axis. A very little intimacy between the nucleus and these electrons. That is why these electrons are held less firmly, loosely between the atomic nuclei, or these electrons are mobile. That is why this bond formed is very weak, and this weak bond is called pi bond. A pi bond is formed only after the formation of a sigma bond. First a sigma bond formed, then the remaining orbitals containing unpaired electron, they overlapped in a sidewise manner, and that give rise to a pi bond. And these are the two different types of covalent bond, sigma and pi. Head-to-head overlap, sidewise or parallel overlap, maximum overlap, minimum overlap. The electrons are present in the nuclear axis. Electrons are not present in the nuclear axis in the pi bond. So a very strong attraction between the nuclei and the electrons. That is why these sigma electrons are localized. They are locked in between two atomic nuclei. They are not mobile, and that bond becomes strong where sigma electrons are localized. But pi electrons are mobile. They held less firmly between the atomic nuclei, or they are mobile, they are delocalized. So pi electrons are delocalized, and the pi bond is very weak. And this is about two different types of covalent bond, sigma and pi. Two different types of orbital overlap. So covalent bond is formed by orbital overlap. It is either in a head-to-head manner or sideways manner. Head-to-head give rise to sigma and sideways give rise to pi bond. Okay. So again VBT in polyatomic molecules. VBT in polyatomic molecules. We can take simple example polyatomic molecules. We can take simple example methane. CH4. 4 bond pairs around carbon. A pair, and a pair. So 4 covalent bond. So according to Pauline's letter theory, any covalent bond is formed by here 4 covalent bonds. So far we discussed hydrogen, only a single bond by SS overlapping. Fluorine, only a single bond. Hydrogen, a single bond by SS overlapping. Fluorine, a single bond by PP overlapping. And hydrogen fluoride, a single covalent bond by Sp overlapping. This molecule consists of 4 covalent bonds. Each covalent bond is formed by an overlapping. So we can find out what is that overlapping. 1 electron of carbon, 1 electron of hydrogen. 1 electron of hydrogen, 1 electron of hydrogen. So 4 covalent bond. How these 4 covalent bonds are formed? By which overlapping? Whether they are same type or different type. So we can discuss about methane, formation of methane. So the central atom carbon with 4 electron, carbon is tetravalent. Carbon is tetravalent. 4 electrons are involved in the covalent bond formation and its valency 4, carbon is tetravalent. So carbon, formation of methane, valence bond theory. In the case of polyatomic molecule, general thing, orbital overlap. Covalent bond is formed by orbital overlap. Okay. Methane, central atom carbon. Atomic number 6. Electronic configuration 1s2, 2s2, 2p2. So valence orbital. This determines the valency. 2s2, 2p2, 4 electron. 4 electron in the valence shell. 1, 2, 3, 4. So this electronic configuration is called ground state electronic configuration, means before the approach of H atom. Carbon atom is in the ground state. Before supplying energy, H atom is not approached and carbon is in the ground state. Ground state electronic configuration. Ground state electronic configuration. Carbon. So 2s2 orbital, 2s2 capacity 2, and this is a 2p2 p shell containing 3 orbitals. So far discussed 2px, 2py and 2pz, 2px, 2py and 2pz. So 2p2 according to Hund's rule. This is wrong. Pairing of electrons do not take place as long as there is a vacant orbital. So 2p2. Pairing do not take place. This is the ground state. So orbitals with almost same energy, 2s and 2p2. These are valence orbitals, almost with same energy, slight energy difference between s and p, only slight energy difference. So this is the ground state electronic configuration. 2s2, 2p2. The 2pz is vacant in the ground state. So fulfilled orbital. The maximum capacity of an orbital is 2 and this orbital is fulfilled. No combining capacity. Orbital half filled. Half filled. These 2 orbitals have combining capacity because they are half filled. So in the ground state, Only two orbitals can involved in covalent bond formation because they are unpaired. So a covalent bond is formed by the overlap between orbitals containing unpaired. So two unpaired. Valence should be 2 in the ground state. But carbon is tetravalent. So what happens? So when hydrogen approaches, when energy supplies, and this s electron, 2s, one of the s electron promoted to the vacant 2p level. When energy is applied, when hydrogen atom approaches, and that state is known as excited state. So excited state, electronic configuration. So 2s2 becomes 2s1, only one electron. So 2px1, 2py1, 2pz1. 2px1, 2py1, 2pz1. Half-filled, 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 half-filled. 4 unpaired electrons. 4 unpaired electrons. Carbon. 4 unpaired electrons. 1, 2, 3, 4. 4 electrons in the valence shell. Becomes free 4 electron. So valency becomes 4. 4 orbitals can combine. Carbon becomes tetravalent in the excited state. So we can again discuss the formation of hydrogen. 4 H atoms are approaching. So S1 electron, this electron is present in the s orbital, 1 electron. And 1 electron is present in the 2px orbital. I marked here this electron. Suppose it is in the 2px orbital. And this electron is in the 2py orbital. And last electron is in the 2pz orbital. So outermost shell of carbon, again this is the key point. 4 electrons are present in 4 different orbitals. So in the beginning, during the formation of H2, F2, HF, we discussed a covalent bond is formed by orbital overlap. So this orbital 2s with 1 electron, 2px with 1 electron, 2py with 1 electron, 2pz with 1 electron. Who is approaching H atoms? 4 H atoms. This is H atom, 4 H atom. Hydrogen atom atomic number 1. Configuration 1s1. 1s1 means spherical orbital with 1 electron. So first hydrogen atom, CH covalent bond, this covalent bond, according to simple valence bond theory, how this covalent bond is formed. H will approaches with its 1s1 electron. 1s1 electron. H atom. This is also s1 electron. This is also s1. H atom approaching with its s1 electron. Daughter point. A covalent bond is formed. This covalent bond is formed by which overlapping? SS overlapping, strong overlapping, maximum overlapping, and the C and the H come very, very closer. Hydrogen, carbon in the excited state, S1 electron, S1. H atom with the S1 electron approaches. Theory, orbital overlap. Orbital electron, orbital electron. Carbon atom comes with its S1 electron. Hydrogen atom comes with its S1 electron. And a overlapping is formed and a covalent bond is formed by SS overlapping. And another carbon with 2px electron, 2px, and H atom comes with S electron and a covalent bond is formed, and this is sp overlapping. Yes, hydrogen S and carbon px and hydrogen s orbital. Spx overlapping, this covalent bond. Spx overlapping. Similarly, again hydrogen comes with its s1 electron, and this is a 2py electron, and a covalent bond is formed, and this is an pys overlapping. And again last hydrogen atom came with its s1 electron, and a covalent bond is formed. This is S and this is PZ overlapping. So this is methane CH4. In this way, in this simple way, we can expect these two four bonds with different types of overlapping. Yes, atoms come very closer, very closer. S orbital is spherical, so they can make a maximum overlap. And these two atoms come very closer, and this bond length becomes too small. So in methane, this bond length becomes the smallest one because that is SS overlapping. If methane is formed in this manner, and this is SPX overlapping, another type, and this is SPY overlapping, this covalent bond, and the last covalent bond by SPZ overlapping. If according to VB theory, in this polyatomic molecule methane, the overlapping is like this. All the four bonds are not identical. They are with a different bond length. Here, bond length becomes too short because atoms come very closer because of SS overlapping. And they are with a different strength. To break this covalent bond, we have to supply larger amount of energy than this covalent bond. Consider all these are Sp overlapping and this is SS overlapping, and to break this bond, large amount of energy for breaking this bond, we have to supply somewhat only lesser amount of energy. So bond energy should also be different in methane. So Pauli's letter theory, covalent bond is formed by orbital overlap. In methane, the four bonds are formed by this type of overlapping, simple overlapping. In methane, all the CH bonds are with different energy and different length and different strength. But actually, from experiments, it has been found that all bonds are identical. All bonds, equal energy, equal length. All bonds are identical. So what happens in methane? So in order to explain this, all orbitals, all valence orbitals, carbon carrying 4 electrons, and these 4 orbitals carry equal energy and identical in shape. So what happens after excitation? After excitation, there is no direct overlap between atomic orbitals. If atom approach and there is a direct overlap, SS, SP, SP, SP like that, 4H atom. 4H atom approaches towards the carbon and the orbital overlap is like this. S, 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 SS, Sp, Sp, Sp like that. The covalent bond formed are with different length and different strength. But from experiments, it has been found that in this polyatomic molecule, methane, all CH bonds are identical. So this can be explained by valence bond theory by Pauli. So after excitation, what happens? So when hydrogen atom approaches, we supply energy and the atom first undergo excitation. After excitation, these valence orbitals 2s, 2px, 2py and 2pz, these valence orbital undergo a mixing, intermixing. They mixed together. One s orbital and 3p orbitals. They undergo a mixing. I am discussing the formation of methane. Carbon is tetravalent. 4H atoms are surrounding this carbon. So these orbitals are with a different shape, spherical and dumbbell. Their energy are slightly different. Difference in energy, somewhat different energy. 2s and 2p, slight energy difference. And different shape, spherical and dumbbell. They undergo a mixing and they produce 4 hybrid orbitals. 4 hybrid orbitals. 4 orbitals mixed together and 4 hybrid orbital. The orbitals involved are spherical orbital, dumbbell with 1 electron and another 2pz orbital. 2pz. 2p, y, 2p, x, yes. These 4 orbitals undergo a mixing and produces 4 hybrid orbitals. 1, 2, 3, 4. 4 orbitals mixed together and 4 hybrid orbitals are produced. like this. Here 2 lobe. For hybrid orbital, only 1 lobe. This is 1 orbital. Here 2 lobe. After mixing, we got only 1 orbital. 1 dumbbell. So 4 orbital. So 1 s orbital and 3 p orbital. This is spherical and this they are dumbbell. The newly formed orbitals have 25% s character and 75% p character. 1s, 3p. 4 orbitals, different shape, majority dumbbell shaped orbital. So the newly formed orbitals have dumbbell character 75 and spherical character 25%. So this 4 orbital give 4 new orbitals. Each orbital carry 1 electron. And these 4 orbitals are oriented along direction, along the 4 coordinates of a regular tetrahedron. Along the 4 coordinates of their orientation, direction. These 4 orbitals are not arranged, the petals in a flower, not like petals in a flower. Not in this manner, these 4 orbitals. They are arranged 4 coordinates of a regular tetrahedron. Why they arranged along the 4 coordinates of a tetrahedron with bond angle 109 degree 28 minutes? So when 4 H atom approaches, these 4 orbitals becomes paired. These 4 orbitals becomes paired when H atom approaches. So bond to pair repulsion takes place. This pair repels this pair. If these orbitals are arranged like petals in a flower, this orbital and this orbital undergo Coulombic repulsion and that methane molecule becomes highly unstable. So to minimize the repulsive force between bond pair and bond pair, the newly formed orbitals are arranged in space in such a manner that repulsion is minimum and the stability is maximum. Repulsion is minimum and the stability is maximum. VSEPR theory. We will discuss later that. Valence shell electron pair repulsion theory. The orbitals will arrange in space in such a manner that here that manner is tetrahedron. For some other molecule it may be trigonal bipyramid. For some other molecule the orbitals are arranged in the 6 corner in an octahedron or in a trigonal bipyramid or a linear manner. So based on the number of orbitals formed, the orbitals will arrange in space in such a manner that here 4 orbital, the manner is the 4 coordinates of a tetrahedron. Why? The orbitals arranged along the 4 coordinates of a tetrahedron with a certain bond angle. For in the case of methane, carbon will arrange its 4 hybrid orbitals along the 4 coordinates of a tetrahedron. Why? To minimize the repulsive force and to attain a maximum stability for that molecule. Otherwise, the bond pair undergo electrons carry negative charge and pair undergo repulsion, and due to this Coulombic repulsion, molecule becomes highly unstable. So in all covalent molecules, during their formation, the central atom will undergo a hybridization. Here the hybridization is Sp3 hybridization because 1 s orbital and 3 p orbitals are involved. If the hybridization is Sp3, in most of the cases, if the hybridization is Sp3 and the lone pair of electrons are not involved, we will discuss it later. In most of the case, after Sp3 hybridization, 4 orbitals are produced. Not only carbon, any other atom, if it undergo Sp3, 4 hybrid orbitals. 4 hybrid orbitals are oriented along 4 coordinates of a tetrahedron in order to minimize the repulsive force and to attain maximum stability. For each molecule, different orientations are possible for their orbitals depending upon the number of orbitals formed. Here 4 orbitals. So the hybridization is Sp3 and 4 orbitals. All are with the same energy. Sp, Spx, Spy, Spz. Not like that. All the 4 electrons are identical. They are present. And this orbital is called, each orbital is called Sp3 hybrid orbital. Sp3 hybrid orbital. Sp3 hybrid, 4 Sp3 hybrid orbital. Formation of methane, H atom is approaching. Atomic number 1, configuration 1s1. spherical with one electron, overlapped here. A covalent bond is formed. CH covalent bond. What is the overlapping? Sp3 S overlapping. Okay. And second hydrogen here. Sp3 S overlapping. All overlapping are identical. A covalent bond is formed by the orbital overlap. Hydrogen atom again containing unpaired electron, another hydrogen atom with one electron. Orbital overlap, Sp3s. Last hydrogen. Orbital overlap, Sp3s overlapping. Four overlapping are similar. They are with the same bond length, same bond energy. And this phenomena is called hybridization. And methane is produced. What is the shape of methane? The central atom. What is the orientation of the central atom? That determines the shape. And what is the hybridization state of the central atom? Carbon. Sp3. Orientation along the four corners of a tetrahedron. So, shape of a molecule, stereochemistry, geometry of a molecule is determined by the orientation of the orbitals. Central atom, how the central atom will orient its hybrid orbital. Here, the four corners of a tetrahedron, that is why the shape of methane is a tetrahedron with a bond angle 109 degree 28 minutes. And that is the valence bond theory. How a covalent bond is formed? In the case of a simple diatomic molecule, simple overlapping, SS, PP, SP. In the case of polyatomic molecules, the orbital overlap is inward is hybrid with the incoming atom's orbital. Here incoming atom is hydrogen, hybridization is Sp3, so Sp3 S overlapping. So covalent bond can formed by hybrid orbital also, like the normal orbitals. Here it is Sp3s in the case of methane. All the bonds are identical, bond strength is same, bond length is same, and confirmed the experiment by means of this theoretical explanation by Linus Pauling and later the VBT. So what is hybridization? Intermixing of atomic orbitals. Intermixing of atomic orbitals of same atom. Here atom is carbon. So hybridization is not the mixing of orbital of one atom with the orbital of the another atom. Valence orbitals of the same atom, here carbon. So it is not between the orbitals of carbon and hydrogen. It is the intermixing of orbitals, the valence orbitals of an atom. So hybridization is the intermixing of atomic orbitals, atomic orbitals of a same atom having slightly different energies and different shapes to form new orbitals, four new orbitals, carbon, four new orbitals with the same energy, same shape, all are with the same shape and the same number, 1, 2, 3, 4, 1, 2, 3, 4. Same number is called hybridization. So what is hybridization? Intermixing of atomic orbitals of same atom having slightly different energies and different shapes to form new orbitals. The same shapes, same energies and the same number is called hybridization, and this hybridization is called Sp3 hybridization. So we discussed the three different types of overlapping, SS, PP and Sp, and different types of hybridization. There also we can see some different types of overlapping also. Here it is Sp3s, first hybridization Sp3 and the four orbitals, four corners of a tetrahedron. Why the orbitals arranged along the four corners of a tetrahedron? Means to minimize the repulsive force and to attain a maximum stability. Theory is called VSEPR theory. We will discuss in another class about VSEPR theory. We can discuss another hybridization taking a suitable example, BF3, boron trifluoride. So valence bond theory, VBT again. So orbital overlap. Orbital overlap. Two orbitals come closer and overlap together to form a covalent bond. A polyatomic molecule, boron trifluoride. Second molecule. First we discussed the methane. Shape tetrahedron, bond angle 109 degree 28 minutes. Tetrahedron, shape tetrahedron, bond angle 109 degree 28 minutes, and CH overlap, Sp3 S overlapping, 4 CH overlapping, 4 Sp3 S overlapping in methane, CH4. We discussed the first molecule, methane. 4 CH bond, 4 CH bond are formed by 4 Sp3 S overlapping. Methane, carbon hybridization, Sp3. Shape of methane, tetrahedron. Angle in methane, 109 degree 28 minutes. 4 CH bonds are formed by which overlapping? Sp3 S overlapping. All are identical, equal bond length, and everything is okay. Hybridization Sp3. The second molecule. Boron trifluoride, second molecule. Boron trifluoride. So this is the structure. I draw like this the structure. 3 covalent bonds. So 3 covalent bonds. How these 3 covalent bonds are formed? These bonds are identical, equal strength, equal length. So central atom boron. So we are discussing about these 3 covalent bonds. BF, 3 BF bonds. So central atom boron. So trivalent. So it belongs to 13th group, boron, aluminium, gallium, indium and thallium. 13th group, outermost shell contains 3 electrons. Outermost shell contains 3 electrons. And boron, atomic number 5, 1s2, 2s2, 2p1. Second shell is the outermost shell, valence shell. So 3 electrons. So electronic configuration is called ground state electronic configuration. Ground state electronic configuration. Ground state electronic configuration. So out valence shell alone. So valence is determined by the valence shell, outermost shell. 2s2, paired orbital, and 2p1. So 3 orbitals in 2p subshell, 2px, 2py, 2pz, 1 electron. Fulfilled, no combining capacity. Half filled, a combining capacity. So only 1 combining capacity. Valence should be 1. But actually boron is a trivalent. Boron is 3 electrons are free. Here only 1 electron is free. This is a paired orbital. So when fluorine atom approaches or when energy is supplied, boron becomes a trivalent by promoting this 2s electron to 2py level. So that state is known as excited state. So excited state. (2s1). 2px, 2py, 2pz, so 3 electron. So these are the 3 electron boron. So to make identical bonds, boron undergo, this is s orbital, this is p orbital, this is also p orbital, different shape, slightly different energies. So all these orbitals are identical. That is why boron undergo a hybridization. That hybridization is called Sp2 hybridization. 1s and 2p. Earlier we discussed Sp3 hybridization. Here Sp2 hybridization. 3 orbitals. So to minimize the repulsive force between the bond pairs, 3 orbitals. 4 orbital means along the 4 coordinates of a regular tetrahedron. Here 3 orbitals along the 3 coordinates of an equilateral triangle. This becomes an equilateral triangle with a bond angle 120 degree. 120 degree. Total 360 and this is 120 degree. Minimize the repulsive force. Boron atom ready. All orbitals are with the same shape. Boron is ready. It combines with any other atom. Here approaching atom is fluorine. Here approaching atom is fluorine. So it is ready. It's 3 orbitals are with equal energy and same shape, dumbbell. And this orbital is called Sp2 hybrid orbital. Sp2 hybrid orbital. So next incoming atom fluorine. You know earlier 1s2, 2s2, 2px2, 2py2, 2pz1. This is the unstable orbital half-filled. Half-filled 2, 7. Shortage of 1 electron to become stable like that of neon. Shortage of 1 electron. The shortage will fulfill when it overlaps with the boron. So 2p is a dumbbell with 1 electron. So dumbbell, fluorine atom with a dumbbell with 1 electron came and overlapped fluorine. So this is sp2 and this is p. sp2 p overlapping. sp2 p overlapping. sp2 from boron and p from fluorine. sp2. Another fluorine came here. 3 fluorine atom. Extend this line. Another fluorine. Another fluorine. Another fluorine with this p orbital. Came and overlapped like this. Another fluorine. The third fluorine. BF3. Third fluorine overlapped here. All overlapping are sp2 p overlapping. sp2 p overlapping. Orbital overlapping are same. So same bond strength, same bond length, and BF3 is produced. BF3 is produced. That is also triangular planar. This bond angle is also 120 degree, and this is BF3. BF3. So boron undergo which hybridization? Sp2 hybridization. So shape triangular or planar. Shape planar. Bond angle 120 degree BF3. So in BF3, BF covalent bond is formed by which overlapping according to VBT? Sp2 P overlapping. So we discussed the SS, Sp, PP, Sp3S, and this is Sp2P overlapping covalent bond. Overlap between orbitals. Here one of the orbitals is hybrid. That's only the difference. Orbitals carrying unpaired electrons with opposite spin. Here one of the orbitals is hybrid and another is pure orbital. Unhybrid orbital. Sp2P overlapping. So shape planar, bond angle 120 degree, hybridization Sp2 central atom boron, orbital overlap Sp2P overlapping. Orbital overlap we are discussing. Different types of orbital overlap. That is the key point of valence bond theory by Linus and Slater, 1932. And this is Sp2 hybridization. So you define Sp2, 1s number, 1s and 2p orbitals, 1, 2 are involved in an intermixing. Hybridization is called Sp2. Here 3 hybrid orbitals are formed. 3 hybrid orbitals are formed. And these orbitals are oriented along direction. Oriented along the 3 coordinates of an equilateral triangle with a bond angle 120 degree. Equilateral triangle with a bond angle 120 degree. That is Sp2 hybridization. Suitable example, boron trifluoride. So far we discussed the 2 hybridizations, Sp3 and Sp2, 2 different hybridizations. So we can discuss another molecule. We can discuss another molecule and another hybridization. So far we discussed the 2 hybridization, Sp3, Sp2, 2 molecules, methane and boron trifluoride. In this similar way, we can discuss the BCl3, boron trichloride. Then instead of fluorine, who will come? Chlorine atom. So same p orbital, but it is a 3p orbital, 3s and 3p. Outermost shell of chlorine, 3s2, outermost of chlorine, 3p Z1. 3pZ1 instead of 2pZ1. That is only the difference. The figure is like this. Instead of fluorine, chlorine will come. Chlorine, chlorine, chlorine. Sp2p, Sp2p is similar. Similar bond angle, similar shape, no difference. P orbital. 3pZ1 will come. Here it is a 2pZ1. Atomic number chlorine. You check the configuration. You check the valence shell and check the valence orbital. The valence orbital is 3pZ1 in the case of chlorine. In the case of bromine, what is the orbital? 4pZ1. So p orbital, Sp3p. So boron trihalide, BX3. Shape planar, bond angle 120 degree. Hybridization Sp2. Okay. So we can take another molecule. T point orbital overlap. Okay. Yes. Beryllium difluoride. So we can take fluoride also. Beryllium difluoride. This is the molecule. And beryllium difluoride, another molecule, 2 covalent bonds. So first we discussed the 4 covalent, then 3 covalent, 2 covalent bonds. Central atom, beryllium, a pair, 2 covalent. How these covalent bonds are formed? By means of which orbital overlap? That is the key point of VBT, Linus Pauling and Slater. Yes, beryllium. Atomic number 4, configuration 1s2, 2s2 and 2p0, and this is the outermost shell, 2s2, 2p0. We have to expand the valency, that is why I showed this 2p orbital also, 2s2, 2p0. Ground state electronic configuration. So 2s2, paired, fulfilled. The ground state, no combining capacity, fulfilled. Fully filled. 2px, 2py, 2pz, empty, 3 orbital, 2p0. So no combining capacity in the ground state, but actually it is bivalent. So you know, undergo excitation in presence of an external energy source, it undergo hybridization. So excited state electronic configuration. So 2s2 becomes 2s1 and 2px, 2py, 2pz, 2px, 2py, 2pz, 1 electron. So 2 half-filled orbital, 2 unpaired electron, so 2 combining capacity, so valency 2, and these orbitals undergo an intermix. Hybridization is called Sp hybridization. Sp hybridization. And 2 orbitals, so 2 new orbitals are formed. So 50% S character, 50% P character. Dumbbell 50%, spherical 50%. 50-50, the hybrid orbital, beryllium. So they are oriented along a straight line. They are oriented along a straight line. 1 electron, 1 electron. These 2 orbitals are oriented along a straight line to minimize the 2 orbitals. In order to minimize the repulsive force between electrons in the orbitals, atomic orbitals, the orbitals are oriented along a straight line with the bond angle 180 degree. Linear 180 degree. Then incoming atom fluorine. Discussed so far. Fluorine atomic number 9. Again, once more. So 1s2, 2s2, fulfilled, 2px2, 2py2, 2pz1. This is the unstable orbital that will come and overlap. A fluorine atom is approaching and overlapping like this with 1 electron fluorine. Another fluorine will come here and overlap with here. 1 more electron. So fluorine. and BF2 is formed. BF2. This overlapping, SpP overlapping. This is also SpP overlapping, beryllium fluorine overlap, same overlap. SpP overlapping, SpP overlapping. Equal length, the equal energy, 2 bonds because of the central atom hybridization. So the new hybridization is Sp hybridization. Third hybridization is Sp. Suitable example, beryllium difluoride. So one S and one P orbital are involved in an intermix. That hybridization is called Sp hybridization. Here 2 hybrid orbitals are formed. Orientation along a straight line with a bond angle 180 degree. That is Sp hybridization. So 3 hybridization, 3 orientation, tetrahedron, equilateral triangle and linear. Why? The central atoms arranged in this manner in order to minimize the repulsive force and attain maximum stability for the molecules. And these are the 3 hybridization, Sp3, Sp2 and Sp. Tetrahedron, planar and linear. So BF bond is formed by which overlapping? Sp-P overlapping. This is about BBT and 3 molecules. We discussed only about a sigma bond, only head-to-head overlap. So we have to discuss the formation of pi bonds, the parallel overlapping pi bond formation, as well as orbitals involving d orbitals. Here no d orbital is involved. S and P, orbital involving d also. We have to discuss in some other classes, and also about the hybridization involving LP, lone pair of electrons. And this is only the basic of hybridization. So thank you very much.